Hello everybody, Mr. Eck here, you're watching EckMath. Today we are talking about section 2.3, which is all about sketching the graphs of polynomials. A quick review of all of our terms that we're going to be using today. We saw these last time in Chapter P, so this is our just quick review. Go back to our Chapter P video if you want more details. A polynomial is going to be any function or expression of the following form. F of x equals a sub n, x to the n, plus, that's the first term, a sub n minus 1, x to the n minus 1, plus, and we can keep going, and eventually we get to a sub 2x squared, a sub 1x, and a sub 0, x to the 0. So we can have any number of integer exponents, but the key rule for polynomials, at least, is that these have to be positive integers. So no fractional exponents. The coefficients can be any real number. They are not restricted to being whole numbers. They can be fractional. Most of the time they'll be whole numbers, but they don't have to be. Degree is, in the polynomial that I've written, the degree is n. And what I mean by that is it's the highest exponent on x, with the catch that that's in multiplied form. Which is the form I wrote up there. So if you see something in factored form, you have to count up and find the degree. You can't, it's not just the highest exponent. But in that form, the n there is the degree, and the leading coefficient is the an, and it's the coefficient of the highest power of x. It turns out that when we're graphing these things, there is, of course, all of this stuff going on in a polynomial, but the most important thing in a polynomial is the first term. So that degree and that leading coefficient tell us almost everything we would ever need to know about the graph. So being able to identify those is probably the most important thing in a polynomial. So just to do two quick examples of degree and leading coefficient. In example 1, this is in that sort of standard polynomial form. So the degree, I just look at the exponents and I look for the highest exponent. The degree is going to be 5. And the leading coefficient, I'm going to find that degree 5 term and look at what is multiplied to it. The leading coefficient here is negative 3. That's not so bad. When you see a polynomial in that form, pretty easy to find degree and leading coefficient. However, sometimes you get a polynomial in this other form where it's already factored out for you. And this form is actually a huge gift from the problem writer, saying, hey, guess what? You don't have to factor. But you do still have to know the degree and leading coefficient, and you can do this without multiplying out the whole dang darn thing. Just by thinking about and sort of counting up the powers of x. So let's count how many powers of x we have. 1 here, 2, but that's got a squared on it, so that's like 1, 2, 3, and then there's an x here, 4. There's 4 powers of x when you include that square. So if I were to multiply this whole thing out, and please don't multiply the whole thing out, but eventually all 4 of those powers of x would have to come together and make an x to the 4th term as the highest exponent. So the degree in this polynomial is going to be 4. And you can find that without actually multiplying out the terms. The leading coefficient, I'm going to abbreviate that as LC. Again, don't multiply the whole thing out, but think about what would happen if you did. And if you did multiply the whole thing out, all of these x terms would get multiplied by each other. That would give us that x to the 4th. But what would be multiplied onto the x to the 4th? Well, anything that's ever multiplied to an x would also get included in the x to the fourth. So I have a 2 there and a 4 and nothing else. This is like a 1x plus 3. So in the end, I can predict that I would actually have an 8x to the fourth. So the leading coefficient here, just by looking at what all the various coefficients are, would be 8, and specifically positive 8. So you can find degree and leading coefficient without multiplying the whole thing out if you just study carefully and sort of imagine what would happen if you did. So why do we love polynomials? Why are we graphing them now? It is because the graphs of polynomial functions are always both smooth and continuous. That is, you can draw one with by putting your pencil on your paper and not picking up your pencil and just drawing a smooth curve with no corners. So for example, this thing that I just sketched, I put some arrows on each end, that could be the graph of a reasonable polynomial. The features that a polynomial graph will never have are the things that are bad on any graph. A discontinuity, where the graph breaks in two, or is it piecewise, because then this would need 2 equations, right? We'd have to do like a piecewise function to create this graph. And the other thing that a graph should not have is sharp corners. Here, this one has 3 sharp corners. That's more of an art problem. Sometimes when drawing like quadratic parabolas, for example, I draw my parabolas with a corner. Technically, that's wrong. You should be really trying to make sure your polynomial graphs are always smooth, continuous curves. And that's why they're so nice in mathematics. Like, we don't like this gross stuff over here. We actually like these predictable, nice, well-behaved functions. This is a little bit of a sidebar, but I was saying how polynomials are so nice and well-behaved. There's entire branches of mathematics that are all about taking messy functions and turning them into polynomials. And I searched a couple for you. This is actually something you learn about in Calc BC. These are called Taylor series. You can express e to the x as a polynomial, right? We have an x squared, x to the third, and it ends up being kind of this infinite series or series of unknown length with some factorials involved. And you can do the same for cosine. You can express cosine as some odd powers of x added together along with factorials, and you can express sine as some even powers of x added together along with some factorials. We certainly don't need this for this class, although we will at some point learn about this function or sigma notation. But you will definitely use this stuff in Calc, probably BC. And it's a really interesting idea. So polynomials are something we always like because they are predictable, they're well behaved, they have nice features, they have, like we showed, happily smooth, beautiful graphs. And so if we have a messy graph and we can turn it into a polynomial with some trick, we usually want to do so in sort of later on in math. So let's now start talking about the graphs of polynomials themselves and how you can construct them and be more specific about what the graphs look like. So I have prepared here below the graph of a polynomial. And I want to talk first about something we mentioned in class, but it's called the factor theorem. And the factor theorem, super important in this entire section. And it says, it goes something like this. If a polynomial has a 0, root, or x-intercept, kind of interchangeable terms, at x equals c, then the polynomial is guaranteed to have a linear factor of x minus c in its equation. By the way, linear factor just means degree 1, right? So it's not like, so it's x to the first minus c. So if you have a root, you're guaranteed to have a factor. The converse is also true, and I just changed the direction of the statements. If you know the linear factors of a polynomial, you also know the zeros, roots, or x-intercepts. So factors and roots are telling you the same thing. How do I want to use that right here? Well, in this particular polynomial graph, I can see immediately what the zeros are. I've highlighted them, and we'll come back to this graph and mess around with it. But then I could use the factor theorem to say that an equation for this could be, and I could just go through the zeros. So the 0 at -5 would have a factor of x plus 5. The 0 at -1 would have a factor of x plus 1. I'm changing the sign because we have this minus c. The 0 at 1 would have a factor of x minus 1. And the 0 at 4 would have a factor of x minus 4. And I've kind of color-coded those factors to match with their matching zeros. And if I were to multiply those out, I would get a degree 4 polynomial that would guarantee to have those zeros. I wrote could be because there could also be some coefficient out here, so I'll put maybe like an a out front just to say, you know, there could be a 2 or a 5 or a 7 out there. I'll write that a little nicer. But other than that, perhaps missing coefficient, this is the equation of that graph. And look how easy that is. The factor theorem basically tells you everything you need to know about the graph. I want to hop over to Desmos and just kind of share with you some computer-generated graphs. So this is the same file that I used to generate the one we were just looking at, but I can also slide and move the zeros around. And I want you to observe how the graph is effectively determined by the zeros. Like where the zeros are is saying where the graph is. The graph is a smooth curve that more or less just is trying to connect the zeros and swing around. So like the graph would, in this case, the graph starts up here. It hits this 0 at -6, crosses through, goes down, and then it just has to turn around and hit the 0 at -2. Crosses through, goes up. It has to turn right around, hit the 0 at 2, crosses, goes back down, has to turn around, and hits the 0 at 5. So you have to, more or less, have a turning point between every 0, and you have to hit every 0 of the equation. I can show you, for example, the equation I plugged in is just x minus c1, c2, c3, c4. And I have little sliders for my c's. I can also just drag them around. So look at what happens, right? If I make the zeros close together, we have the same behavior. Even if I make these zeros, if I put them really close together, I'd have to zoom in. I'm not going to do it because it took a long time to get the scale set. But the further your zeros are, you can see no matter where they're at, you're still crossing and waving between the zeros. If they're further apart, the graph gets a little off screen, right? Like the graph has to go a long way to curve around. One thing that's interesting on polynomials is look at this scale. The x's going from -10 to 10, and the y's are going from -400 to 400. So the x and y scales are really different, and that sort of makes sense if you stop and think about it for a second. We're dealing with numbers to the 4th power here. 4th powers get really big really fast, so it makes perfect sense that the y values are going to be really big. When we're graphing polynomials by hand, we're pretty much going to ignore the y-axis because the scale is so ginormous. It's not really useful to try to figure out that the y-intercept, I guess like Desmos is saying, it's 24 here. But like if I move this around, to make a little taller of a graph, right? It's not really relevant that the y-intercept is 360. We're not going to try to fit that on our paper. We're really just looking at the zeros and the general shape. Same deal with polynomials. As of now, we have no way of finding this turning point, the actual coordinate. Desmos is saying that it's, right, these crazy decimals, they're probably irrational numbers. You do actually need calculus to locate the turning points. We can know that they exist, we can sketch them, but we don't know their exact coordinates. And so we're not going to be trying to find turning points today. We're just looking at zeros, and we're also going to be looking at the left and right end behavior, which in this case is up and up. So I just wanted to move this around and kind of share it with you. We will come back to this when we start talking about multiplicity, because you can observe some interesting things. Or you might be wondering, what happens if, for example, 2 zeros are on top of each other? We will come back to that. Or what if 3 zeros are on top of each other? We'll come back to that in a little bit at the end. So we've just been talking about how the zeros kind of form the shape of the graph, but there's something else that forms the shape of the graph as well, and that is the end behavior, whether the graph is going up and up, or down and down, or perhaps something like this. So there's actually many different kinds of end behavior that a polynomial could have. And it is very predictable. And here's how we predict. So end behavior is essentially what happens when x is very large or very small. And when I say very small, I don't mean like close to 0, I mean very negative. So effectively, We are asking what happens when x is infinity or negative infinity, the very far left and right extremes of a polynomial graph. I don't want to deal with infinity yet. I'm going to deal with just something like 100 to explore. So here I have a fifth degree polynomial, 2x to the fifth minus x to the fourth plus x plus 3. And I just want to plug in the number 100. So the terms in order would be 2 times 100 to the fifth minus 100 to the fourth plus 100 plus 3. I'm not going to add everything up, but I am going to simplify this a little bit. 100 to the fifth will have 10 zeros. So this is going to be 2 with 10 zeros. 3, 4, 5, 6, 7, 8, 9, 10. That's a pretty big number. Now this thing is going to be pretty big too, but it's only going to have 8 zeros. So I have this 2, whatever that is, minus something with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then to this, whatever colossal number this is, I'm adding 100, and I'm adding 3. And then we kind of want to ask ourselves, like, what term actually matters here? What term matters? The only term that really is important was this leading term. Even if I do on the calculator, I'm just going to do 100 to the fifth minus 100 to the fourth and compare that to 100 to the fifth. Like, it's not very much different. The 100 to the fourth is 200 times smaller than the 100 to the fifth term. So these terms don't matter if x is large. And it would be the same thing if we computed it and plugged in negative 100, wouldn't it? With one small difference. If I did negative 100 to the fifth, it would be negative 2 with 10 zeros. Negative 2 times 100 to the fifth. And then this, now, but look at what happened. What happened here? Negative minus negative 100 to the fourth. That would still actually be, this would actually still be positive because it's a fourth power. 1, 2, 3, 4, 5, 6, 7, 8. Plus those plus 100 plus 3. Oh, it'd actually be minus 100. Again, guess what? None of those other terms matter. None of those matter. Don't matter. Same deal. The only thing that really, really contributes to the size of this polynomial is the 100 to the fifth. And this would obviously be even more dramatic if x was 1,000, right? Like 100's not actually a very big number. 100's pretty small in the context of all numbers. If I had 100 to the 1,000, then the fifth degree term would have so many more zeros that it'd be so clear that nothing else would matter. So when we're trying to determine end behavior, it only depends on your leading term. So 2x to the fifth is the only thing that determines the end behavior of this polynomial. And just to prove that point, I plugged this, just copied it into Desmos. It's not being a very exciting polynomial. That happens sometimes. But I can notice that no matter how far I zoom out, I have to zoom kind of in a non-square way. But if I zoom out a long way in the x, right, to like 1,000 on the x, there's nothing that's going to stop this graph from shooting up to infinity and down to negative infinity as x gets large. nothing stops that. So despite the fact that there is that little wiggle in the middle, as soon as we kind of zoom out our scale, that's no longer really visible. We can, it just starts to look like something going up to the right and down to the left. So the leading term is the only thing that controls that. I could delete all the rest of that stuff and it would not change the essential shape of the graph. Leading term is the only thing that matters. So we would say that mathematically, as x approaches plus or minus infinity, right, left or right sides, the term with the highest exponent starts to dominate or take control. And that term alone is what really controls the shape. And that brings us to a set of tests that are called the end behavior tests. And we'll try to put them all in one nice chart right here. These are sometimes called the leading coefficient tests, but that's, a little misleading. We're going to be looking at two things in our polynomial. So we assume that the leading coefficient or leading term is an x to the n. And the an, the leading coefficient, is going to tell us something, and the degree is going to also tell us something. So if we're going to start with the degree, if the degree is even, for example, x squared, x to the 4th, x to the 10th, etc., then the graph will look like this. There might be some stuff going on in the middle. We don't know what's going on in the middle. We're looking at end behavior, but as x gets larger, the graph will have to trend upwards because the highest degree being even means that we're going to trend towards positive infinity. And as x gets negative, a negative to the an even power also becomes positive. So our graph will kind of look like this. It will have the end behavior that it goes up to the left and right. That's really informal way to say it. So a more formal way to say it would be as x approaches infinity, f of x also approaches infinity. So in this case, I'm saying as x approaches infinity on the x-axis, f of x approaches infinity on the y-axis. And as x approaches negative infinity, that is over here on the x-axis, f of x, i.e. the y values, also approach infinity. That's what happens if your degree is even and you have a positive leading coefficient. The way that I remember this is that this is like x squared, right? I know what parabolas look like. They go up to the left and up to the right. Anything with even coefficients will have the same end behavior as a parabola, or even degree. I said coefficients. I meant degree. Anything with even degree will have the same end behavior as a parabola. What if the degree is odd? So our examples would be x to the 3rd, x to the 5th, x to the 117th, blah, blah, blah. If the degree of your first term is odd, then your graph will look like this. You, again, might have some stuff going on in the middle, right? You could have waves and swoopies, but on the left end, eventually, with a very large x, the graph will shoot up towards infinity. But on the right end, when we're plugging in a negative number, the graph will shoot down to negative infinity. So at infinity on the x, we approach infinity on the y. But at negative infinity on the x, we're approaching negative infinity on the y. So we would say in words, what color was I using? That this graph goes down to the left, up to the right. That's informal. Formally, we would say as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x also approaches negative infinity. So when I write that f of x, remember that I'm saying basically y. What's happening on the y-axis? So that's like x, and that's y. I should keep that. And the way I remember this one is that its behavior is like x cubed. X cubed, what does that look like? It's a squiggle, but specifically it's a squiggle that goes up to the right and down on the left. And anything with an odd degree might have some other stuff going on in the middle, but it's going to share the same end behavior as an x cubed. So if the degree is even, we have the same end behavior as a quadratic. If the degree is odd, we have the same end behavior as a cubic. As long as you know those two kind of basic parent functions, you're going to be great. Now I want to complicate things a little bit because we haven't talked about the leading coefficient yet. These first two items here are assuming, I need to figure out where I stashed this. These first two items are assuming that the leading coefficient is positive. So for example, 3x to the fourth, or nope, yeah, oh yeah, it could be an odd number, or 1,000 x to the third. Those would apply on this first line. But if your leading coefficient is negative, so negative 13x to the fourth, or negative 1,000 x to the third, we're going to have slightly different behavior. It's just going to be a reflection of the behavior I just listed. So for even degree, even, but with an negative, the graph will look like this. You might have some stuff going on in the middle, but instead of shooting up and up, the graph is going to go down and down. So we would say this is down to the left and right. And for odd, if the leading coefficient is negative, you're going to have a reflection of the graph above as well. Now in this case, I'll be going up to the left and down to the right with some other stuff going on, possibly in the middle. And you could also put this in the more fancy notation. I'm not going to do so, but you would just switch the positives and negatives on those infinities. So these are called the end behavior tests. You're looking at the leading coefficient and you're looking at the degree. And if you know that, you can sort of sketch the left and right ends of your graph before you even begin doing anything else. I want to do a little sidebar about notation because there is some new stuff here. Instead of just saying up, left, down, right, there are some formal, official ways to write end behaviors. You know, when you're hanging out with your friends, no one really cares what notation you use. But when you're doing this, you know, in a a formal setting, then you want to use the right notation. So say that I had some graph that had end behavior that I would draw as an arrow towards negative infinity. Right, so something like this. What I would say is as x goes to infinity, f of x goes to negative infinity. That's what I would say with my words. What I would write is, instead of writing out the words goes to infinity, I just write x as an arrow pointing to infinity, and that represents goes to. And I can say the same thing, f of x goes to negative infinity. This is my favorite notation for us in pre-calc. But there is this notation you're going to use C in calc called limit notation. And there's technically a little bit of interesting requirements for limits to be verified to really use this. But you will also see it in our book sometimes. So if it shows up in a question, I want you to know what's going on. It's saying the same thing. So there's this little lim that stands for limit. And the way you look at this math sentence is you interpret it in the same way as the sentence up here. So that I would read this out loud as the limit as x approaches infinity. So the limit as x approaches infinity, that's this piece here, of f of x, and then I say is, and that's what it's equal to. So in this case, I would write, we're going to negative infinity, so I would write equals negative infinity, negative infinity. Limit notation is kind of nice. Sometimes you see it with the arrow right underneath the lim as well. If you want to kind of press yourself and use this notation, I'm fine with it. But personally, for pre-calc, I prefer writing things kind of in this form here. It's a little less formal, and it's more getting you into the ideas. What you want to avoid is trying to show off and using limit notation, but then using it wrong. Because then if you use wrong limit notation, you've communicated the wrong thing about a problem, and we'll probably have to mark that problem wrong. So just watch out for your notation, but be ready when you see these things. And when you see this lim thing, it's not trying to say anything new. It's just trying to say, hey, where's x going and where's y going? Let's do some examples. We've been doing a lot of theory. We have to do some examples, but we now know enough. So this asks us to use the leading coefficient test to determine the end behavior of the graph. So I need to know two things. I need to know its degree, and I need to know its leading coefficient, an. So the degree is like that example we did. We kind of count up the powers of x. So I have 3 powers of x. I have 1 more here and there. So I'm going to have a total degree of 5. And I'll observe that 5 is odd. The leading coefficient, well, I see this 2 out here. And then I'm going to check, are there any other coefficients on x terms? And there's not. So the leading coefficient is 2. And specifically, it's important that it's a positive 2. So the end behavior here is going to be odd degree, positive coefficient behavior. On a graph, that's going to be like x cubed then. Even though it's a degree 5 and there's other things going on, the end behavior, whatever's going on in the middle, it will, to the right, it will rise, and to the left, this graph will fall. And so we know what happens now on the extreme left and right ends just by looking at the degree and the coefficient. In formal notation, I would write as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, that's the left end, f of x approaches negative infinity. So if I was being a little more formal and like putting this into a computer, this is probably how I would describe the end behavior. Later in the video, we're going to come back to this example and finish the graph. So right now, there's a big question mark. What's going on in the middle? We just know about the ends. We'll come back and finish the graph pretty quickly, actually. But to finish a graph, we might need to know, we know the end behavior, we might also need to know the zeros, or we're going to need to know the zeros. So I want to do a little review of factoring. So here, for example, we have some factoring problems. Find all zeros of x cubed plus 2x squared minus 4x minus 8. Ooh, boy. So zeros are things that make the equation 0. Because it's a cubic with 4 terms, this is ripe for factoring by grouping. One thing to remember when factoring cubics like this by grouping is that if you have a negative third term, make sure you group that in the parentheses and put a plus sign in between. It's going to make everything work out much more nicely. So then, when we group out, I can pull out an x squared and get an x plus 2. And then here we'll do plus. Looks like I can group out a negative 4 and be left with an x plus 2. Then these terms can group out as well, like technically because x plus 2 is now a common factor, so x plus 2 is going to come out to the right side. So we'll get x squared minus 4 times x plus 2. And you might at this point say, haha, I'm done. I'd factored it by grouping. I'm successful. But be careful, because we may have to do a secondary step. This is not a linear factor yet. So x squared minus 4 should be factored into x plus 2, x minus 2. And then don't forget that we also carry down the x plus 2 from above. And at that point, we can actually start to simplify even more and write this as, there's 2x plus 2, so write as x plus 2 squared times x minus 2. Now that I'm fully simplified, we'd be ready to graph this. We're also good to find the zeros. Every factor correlates with a 0. So this factor of x plus 2 will have a 0 of x equals minus 2. And the factor of x minus 2 will have a 0 of x equals 2. So the zeros are going to be negative 2 and 2. Again, we're going to come back to this problem in a little bit and combine the zeros, what we know about the zeros, with what we can tell from the leading coefficient test to construct a pretty accurate graph of this polynomial. But for now, this is just a little factoring review. So don't forget factoring by grouping. It's a really helpful trick. Here's another one, factoring, find all zeros. And specifically here, there's sometimes folks get stuck because there's only 2 terms. So we say, well, what do I do? Where do I put the grouping? Look for common factors, right? We have an x squared and an x to the 4th. That already has a greatest common factor of x squared. And then actually, just like before, x squared minus 4 is a difference of squares. So this can factor into x squared, x plus 2, x minus 2. And then these are the factors. So we can find the zeros as well. Now, the x minus 2 term gives us the 0 of x equals 2. The x plus 2 term gives us the 0 of x equals negative 2. And don't forget that the x squared term gives us a 0 of x equals 0. Sometimes people forget that because it doesn't look like x minus something, they forget that that's a 0. Technically, that term is x minus 0 quantity squared, if you want to think about it that way. So the set of zeros are 0, negative 2, and 2. And the degree is 4, so we're going to come back in just a second and combine what we know about the zeros with all of our leading coefficients as well. I want to highlight something really critical that's happened though. In both of these examples, we had a factor in our final factored form that appeared more than once. We had that x plus 2 that had appeared twice in the equation, and we wrote as x plus 2 squared. Additionally, in checkpoint 6 here, we had the x squared term. That's really right, x times x. So that's also a factor that appeared more than once. And a factor that appears more than once actually has a really critical effect on the shape of the equation. And so before we can sketch these graphs, we have to understand what happens when a factor appears, or when factors are appearing different numbers of times. And that number of times a factor or zero appears in a factored polynomial is called the multiplicity of that factor or zero. So, I have prepared for us a really icky, sticky polynomial that has all kinds of things going on. But I want to go through and look at the different factors and count how many times they appear. So, x squared is really x times x. So this appears twice. X minus 1 I only see once, so this appears one time. X plus 1 I also only see once, so that also appears one time. X minus 2 appears 3 times. And we could actually have written this as x minus 2 quantity cubed is how you'll usually see it. So if I were to list the zeros here, and I like to list the zeros in increasing order. So I'd have a 0 of -1, a 0 of 0, a 0 of 1, and a 0 of 2. I could, beneath them, list the multiplicity of each. Multiplicity. By the way, this gives me the x squared gave me the 0 of x equals 0. That gave me the 0 of x equals 1. This gives me the 0 of x equals -1. And this gives me the 0 of x equals 2. That's where those numbers came from. I just rearranged them and put them in increasing order. So -1 had multiplicity of 1. It appeared one time. 0 came from the factor x squared, had a multiplicity of 2. It appeared twice. 1 had a multiplicity of 1. It appeared once. And the x equals 2 appeared 3 times, that had a multiplicity of 3. It's really helpful to put the zeros and their multiplicities in a little chart like this in preparation for graphing. Because obviously here, this is a complicated equation. There's a lot of things going on, and it's not like really in order. So it really helps to help understand what's going on. Now, looking at these multiplicities, I want to go back to Desmos and explore what happens with the different multiplicity potentials of a zero. All right, so we're back in this equation. And by the way, we now know that this would be an even degree polynomial because it has end behavior that's going up and up on either end. That's confirmed by the fact that in the equation there are exactly 4 factors and there are 4 zeros. So hey, we know a little more now, very useful. But I want to start seeing what happens if my zeros are starting to appear more than once. So right now I have 4 zeros and they're all different. That is, they came from, each slider here represents a 0, and they all represent different numbers at this point. But what if these 2 zeros on the right started to come closer and closer together? What if they were right on top of each other? That is, I had 2 factors of x minus 2. Notice what happens to the graph is now it doesn't cross, it actually bounces off of the axis. So we are not changing sign anymore as we travel through this piece of the graph. If I bring them apart, at a 0 of multiplicity 1, the y value will always change from positive to negative. But if you have a multiplicity of 2, or actually a multiplicity of 4, if they're all together, then your sign does not change as you travel across the graph. So even multiplicities are going to represent a bouncing behavior off the axis. Now let's explore what happens with an odd multiplicity. So actually, multiplicity 1 is an odd multiplicity, and you can see that when a 0 appears just once, the graph crosses straight through the axis. But what if a 0 appears 3 times? So I'm going to take 3 of these zeros and drag them right on top of each other. And let's compare. So I have on the left a multiplicity 1, 0. That factor appears just once. But on the right, this factor is appearing 3 times. I have 3 factors of an x minus 3. And for the multiplicity 1, 0, the graph crosses the axis and goes straight through, almost in a linear way. It's just going straight through. But for the multiplicity 3, 0, the graph actually sort of has an inflection point or flattens out before curving back up. Now, is this super important to sketch in your graph? Not super important, but it can help you get the right shape and really understand that multiplicity 3 or more zeros, that is when they're odd multiplicities, flatten out. And they kind of look actually like x cubed. So this is like a little baby x cubed behavior over here. You can get, if I move this far away, you can get it to be really pronounced flattening out as you see how it just gets closer and closer to 0 when we have that factor. So to bring this idea back to the chart, by the way, I'm going to put this Desmos in show notes for you, and if you really, I would really encourage you to play around with it. There's something to be said for just getting your hands on there and dragging the zeros around to see the different shapes. I'd strongly recommend it. But to get back to this notes and talk about multiplicities, there's 3 different behaviors that are going to be useful to know. A 0 of multiplicity 1, we'll make this into a little chart, will cross through the x-axis, and it will look like this. These are all examples of good zeros of multiplicity 1. Those are all examples. Zeros of multiplicity even, that is 2, 4, 6, 8, whatever, are going to bounce off the x-axis. So those would look something like this. So you would touch the axis, but instead of crossing through, you would turn right around. And sometimes when you bounce on the axis, depending on the degree, the sort of size of the bounce is, or the flatness of the bounce is different. That's not super important, but this would be like a higher multiplicity. Gives you kind of a flatter bounce. This would be like a lower multiplicity. So that would be like an example of maybe a multiplicity 2. This would be maybe an example of multiplicity 6 with the different speeds, sizes of the bounce. You can also bounce off of the x-axis from below if you started in the negative side. So you could, for example, do this. Bounce, bounce, bounce a third time, and back down. But you would never cross the axis unless you also had a 0 of odd multiplicity. Zeros of multiplicity 3, 7, or 9, that is factors that occur more than an odd number of times, but more than once, will cross through and flatten out. So an example of that, of a type of 0 like that, would be something that does a little bit of this action. This is not a very good sketch. And that can happen more than once in a function. So if it happens a lot, it looks like a little hat. I don't know. Right, so that's an example. 2 zeros of multiplicity 3 would give a shape like that. Multiplicity 3, multiplicity 3. And again, the multiplicity is the number of times that that factor appeared in the equation. Now that you know about multiplicity, we can actually start to graph some things. So here we go. This is the example from earlier, just a little bit ago. And we looked at the 4 zeros of this polynomial, and we looked at their multiplicities. Underneath the multiplicity, then, I'm going to say its behavior. Just as a note to myself, what happens? So at multiplicity 1, we're going to cross right through the axis. At multiplicity of 2, we're going to bounce off the axis. Multiplicity 1, we're going to cross the axis. And multiplicity 3, we're going to cross and flatten out. Other things that we might need to know about this. The degree. The degree, you can actually, if you have your multiplicities, the degree will be the sum of all the multiplicities. But you can also count directly. And I think I'll just do counting directly. So we have 2, 3, 4, 5, 6, 7 powers of x. So this is going to be degree 7. Most notably, that means it's an odd degree. The leading coefficient, well, there's no really coefficients here. So the leading coefficient is 1, and specifically, it's positive. And combining now everything together, what I know about the degree and leading coefficient, which will tell me that the end behavior will be up to the right and down to the left. So I'm going to combine now what we know about the end behavior and what we know about the zeros to make the graph. Now this graph is not going to be to scale. I don't have my graph paper here, and the y values would not be to scale anyway. So instead, we're just going to kind of sketch it out. The first thing that you're going to plot is all of your zeros. So here is the 0 at -1. Here's the 0 at 0. Here's the 0 at 1. And here's the 0 at 2. Then, pick one end or the other to start with and draw a little arrow. I like to work from the left to the right. So my end behavior says that the graph will be going down in that direction. But now I'm going to work backwards. I'm going down in this direction, but that had to come from somewhere, and it had to come from this 0. Now, as I get towards this 0 at -1, I notice that I said this was going to cross through the axis. So let's cross through the axis. Then we have to turn around, right? We gotta loop back around to get to our next 0. I'm approaching the next 0 at 0. What's going to happen? I said that the graph was going to bounce. So we sketch a curve that bounces right off the axis here. Turns around, comes back up. I'll pause right now. We don't know exactly how to find the turning points, so just guess. You need to find the exact turning point. You need calculus, and I'm not teaching you calculus today. Sorry. Wait for next year. But it's also freeing. We're really just sketching this curve. Okay, so I got to turn around, maybe I'll make this one a little higher, just for funsies. And as I approach the 0 at 1, I've said that the graph needs to cross the axis again. So we'll cross straight through, and then start to turn around. And I notice that as I cross this last axis, I need to cross and flatten out. So I'm not going to go straight towards the 2. I'll go a little, undershoot it a little bit so I can flatten out, hit that 2, and then go straight up. And that is going to be a pretty good estimation of the graph of this polynomial. By the way, as a check, I ended up going up on the right, and that's what my end behavior had said. So I'm going to check at the end, does my end behavior agree with what I calculated in the end behavior test? And if it doesn't, well, I have some work to do. I just copied that equation. I'm going to paste it into a blank Desmos window. Let's see if our graph was correct. Okay, here's what Desmos says. We cross, we bounce, we cross, and here you can see that crossing and flattening out behavior. The only thing, if I tab back, that we were wrong about is we were wrong about the height of this little hill. Everything else was pretty darn close. And like I said, there's no way to know the actual height of that hill other than plugging in points or using calculus. And we are not going to ask you to do either. We're just making a sketch. So this is a pretty capable sketch of this graph altogether. So we're going to close this video not by doing new problems, but by going back to all of the old problems and finishing their graphs. So we previously did checkpoint 2, which was about 2x cubed, x minus 1, x plus 5. We determined that the end behavior was going to be odd and positive, so up to the right and down to the left. Now let's go ahead and look at the zeros and their multiplicities. So the zeros, if I make a little zero chart, 0, multiplicity, and behavior. I'll have a 0 of -5, and that appears one time, so it has multiplicity 1. I'll have a 0 of positive, I want to go in increasing order. I'm going to have a 0 of 0, and that appears 3 times because it's an x cubed, so that's multiplicity 3. And I'll have a 0 at positive 1, that appears 1 time, multiplicity 1. The behavior then at each of these is going to cross, and flatten out, and cross again. So I've got my end behavior, I've got my zero chart. That is enough to construct a fairly reasonable sketch of the graph of this polynomial. Plotting out the zeros, the first one is at -5 over here. The next is at 0 itself. And I have another 0 at 1. It's not quite to scale. I'm giving myself some space to draw in here. I also said that the end behavior was down and then up, so I can kind of put an arrow there and an arrow here and start to work to connect them. And then we just pick a direction to go. So I will start with the left arrow and finish the graph. So I'm coming up to the 5, and I'm going to cross at the 5. Then, continuing a smooth polynomial curve, it's going to turn right around. And as I approach 0, it has to cross and flatten out, is what I've said. So I'm going to try to kind of cross towards 0 with a little bit of a squiggle there. And then, smooth polynomial curve has to turn back around, cross at 1 again. Crosses at 1, heads on through. I'll just redraw that arrow. And the end behavior on the other side agrees with what we said we should have. So we have the correct left and right end behavior. We have the correct behavior at the zeros. That's a pretty good graph of f of x, or at least a sketch. In this next problem, we were finding the zeros. So we already know what the zeros are, and we can look at their multiplicities. I also need to know the end behaviors. So the degree is going to be 3, and the leading coefficient is 1. So this is also going to have that odd end behavior of up to the right and down to the left. I hope our next example is even. If not, we'll make another one that's an even one so we can show you that. But it's going to have this kind of behavior. So I know the end behavior. Let's make a zero chart. So my zeros I had a 0 of -2 and a 0 of +2. The factor of x plus 2 had an exponent of 2, so that's going to be repeated twice. That has a multiplicity of 2. The 0 of x equals 2, that factor only appeared once, so that has a multiplicity of 1. So the behavior is going to be a bounce and then a cross. And there's no weird flattening behavior here. Now, that's enough information to sketch the graph. All right, so I kind of have two important pieces of information. The zeros are at -2 and 2. Be a little more symmetric than that, though. There. The end behavior has to be down and then up. So I'll try to match those zeros. But I'm bouncing at -2. So I hit -2 and then I turn around without crossing the axis, bounce down. Smooth polynomial turns around somewhere. Again, don't worry about getting that turning point precise. Comes up, approaches the 0 at 2, and crosses right on through the axis. And my end behaviors match with the degree and the leading coefficient. So this is, again, a pretty good estimation of the graph of that polynomial. One more thing you can do, you don't have to do this, but it can help on a graph like this, is because I was given this form, x cubed plus 2x squared minus 4x minus 8, it's pretty easy to compute f of 0 and find the y-intercept, because f of 0 is just 0 plus 0 plus 0 minus 8. So I could tell that this point is minus 8. And that's just like kind of good evidence, right? If you're not sure exactly how to make the curve, get that minus 8 on there and it'll help out. But I don't think it's necessary. It's just another helpful thing. All right, and finally, checkpoint 6. We found the factors and zeros of this. So I know the factors and zeros. And I'm actually just going to work right from here. So I knew the zeros. Their multiplicities of x equals 0 has multiplicity 2 because that factor appeared twice. These multiplicities will both be 1 and 1. Those factors only appear once. So the behavior is going to be a bounce, a cross, and a cross. I also know that the degree is 4 and the leading coefficient is 1. So the end behavior is going to be up to the left and up to the right. So now, like before, I know the zeros, I know the behavior at the zeros, I know the behavior at the ends. That's enough to make the graph. So I have -2, 0, and 2. There's no point finding the y-intercept because the y-intercept is 0 here. We'll do this one in green. I'm feeling green today. So now I have up and up behavior that I have to match. Let's see what we get. So at -2, we're going to cross the axis. So come down, smooth curve, cross. Ooh, pen's being wiggly. Cross the axis. Then turn around, come towards 0. And at 0, we have to bounce. So we're going to get up to 0. Bounce back off, then turn around, go for the next one. As you approach 2, we notice we're going to cross the axis, and as we cross the axis, we can join up with what we knew the end behavior was going to be. So the left and right ends can match. And that, my friends, is how you graph a polynomial. You factor it to find the zeros, you look at the leading coefficient, you look at the end behavior. That tells you everything you need to know along with bouncing and crossing. But basically, once you have plotted out the zeros, graphing these things is nothing more than connecting the dots in the right order. And I find it very satisfying and a lot easier than it seems at first. There is one more thing that I wanted to cover, I think I put at the very end, and it's 2 final graphing ideas that can help you understand or check on the shape of your graph. So one of them is that the degree of a polynomial is the maximum number of zeros that you could ever have, right? If I have an x to the 5th plus blah, 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 eventually I'm only ever going to be able to factor this into 5 terms, because I could have, right, an x, 5 different x factors. There's no way that I could have a 5th degree that has 6 zeros, because then I would actually be a 6th degree. So the degree tells you a maximum number of zeros you can have. The reason it's a maximum and not an exact is that I could have repeated factors, and then it would be less. That's why the degree tells you the maximum number of zeros. Related to this is the idea that between each zero, so we're talking about plotting out the zeros and connecting the dots, the only time a graph is going to turn around is when it has to turn around to get the next zero. Maybe you bounce, right? You can still bounce, but you still have to turn around in between the zero. So the maximum number of turning points is 1 less than the maximum number of zeros you can have. So say that I had an x to the 10th plus a lot of other things, I would know that that would only be allowed to have 9 turning points. This isn't a particularly useful fact as long as you're not trying to get like weird with your graphs. But basically it's saying is if you're graphing an x to the 3rd and you have a couple zeros, don't get fancy and try to go like, well, Mr. Eck, I'm just going to throw some squiggles in there and then finish my x to the 3rd. If you do something like that, that will violate this. Otherwise, though, it's not really a useful, that good of a fact for graphing, but it is a nice check on your graphs. So just, things to think about with graphs. Okay, we've been here a long time. Thank you all for watching. I hope this has been helpful and enlightening. Please let me know what questions you have. Enjoy your homework. Good luck, and I'll see you all next time.